Yes, it's good to be here, and fortunately I've got other business on the East Coast, and we happen to schedule this when Jay was in town and I could be available, so it's good. I think with this cozy environment, if I get in your way, just tell me and I'll move to the other side. And a copy of this presentation was sent to Jay and Dee.
Already posted.
Already posted, good. There's a report that I'm going to be sending Jay on a memory stick shortly that has a lot more technical details. In an hour or so, I can't get into a lot of technical details, but I just finished writing a very big strategic plan for EPRI and the electric utility industry in this country, and there's a lot of good information in that report. What I'm going to present today is first a little cartoon that sort of tells you why we're here. I'll let you read it. I thought I'd get your attention while you're eating. The big issue is that the electric utility industry, like many industries over the course of time, have actually created not only a lot of benefits to society, but a lot of problems for society. And the big problem today, and certainly for the next probably 50 years or more, is related to CO2 and how to transform the electric industry to be more efficient and to reduce its emissions of carbon dioxide. There's a lot of other technical issues that also have had benefits as well as disbenefits. And what this cartoon sort of indicates is that we need to come up with a different way of thinking. And one way to do that is to bring in new graduates from fine universities like this. And over time, I'm hoping that the next generation will in fact correct some of the problems that the previous generation caused, but also respect the fact that there was a lot of benefits that the previous generation produced as well. Too often children, even my own, say that I'm giving them an inheritance that is going to be very troublesome, but I've also given them some benefits that sometimes they forget about. What I'm going to talk about today is just a little brief overview of the electric system based on some comments that Jay gave me this morning when I sent him this copy of the presentation. I found out that most of you, ladies and gentlemen, probably know a lot about the electric system of this country, so I won't spend too much time on it. What is the role of the Electric Power Research Institute in R&D? Some key drivers. This report, we started what was called scenario-based strategic planning. I'll discuss that briefly. Some R&D opportunities that may even be useful to you or some of your colleagues in writing dissertations. Some very brief examples of some of the work that EPRI has done. We have over 1,000 running projects at any given time, and I'm just going to show you 4 or 5. So there's projects and reports that are open to the public, in most cases available to you if you get online and look for them. And then there's
we should probably mention we, for any research, have access to essentially all of the EPRI reports.
Good.
If you find one,
yeah.
Go to me or Granger.
So what you'll find if you get on the web and you take advantage of some of the websites that Jay just talked about, there's more than enough information. What you have to be is very selective when you do your searches. And knowing students, you're familiar with Google searches, and if you don't get selective, you're going to end up with 1,000 returns, and that in itself can be a problem. And then lastly, I'll talk a little bit about some of the opportunities at EPRI in employing some new students. This is a picture of the first privately owned research laboratory anywhere in the world, actually. And this is the Tom Edison lab in Menlo Park, New Jersey. And Tom Edison is sitting right there. This is where the electric light bulb was invented. It turns out after Tom died, his good friend Henry Ford moved this entire building and laboratory to Dearborn, Michigan. So that's where you can find it today. And this picture was taken somewhere around 1880, or February 1880, and the first light bulbs, can't quite see them here, this is one of them and this is another one, were retrofitted into a gas lighting system that was in this building when he first bought it. Another thing you may want to be interested in is Tom Edison used to play the organ back here while his workers did their research. I don't know if you have that perk here, I doubt it.
We got iPods. It's all right.
I see, okay. Okay. Tom Edison in his 60s is pictured here, but there were other great men, many others, that contributed to the development of the electric infrastructure in the United States and worldwide. This is the famous Nikola Tesla, which really invented the AC polyphase system we know of. This is George Westinghouse. Here's a gentleman who doesn't get too much credit. His name is Charles Steinmetz, and he was a German mathematician and ultimately became head of the computational department of General Electric. And you can give him the credit for the square root of -1 and applying that mathematical principle to magnetic field calculations. And it wasn't until he came along that we could actually model properly AC and as well as DC induction motors and synchronous motors. This is a picture of the world. It's sitting back here on this wall, and it sort of gives a quick idea of the benefits of electricity across the world. And I'm sure that Tom Edison probably would be quite surprised, not only to be in space like Jay has been, but to see the electric light bulb being so prolific across the world. And I'm sure he'd be very, very pleased. He certainly had the idea of commercializing electric lighting across the world. In his own time, he financed the development of an electric lighting company in Paris soon after he invented the light bulb and showed it to the public. Midnight, New Year's Eve, 1879 is when he showed the light bulb to the general public in Menlo Park, New Jersey. I won't get into this, but you should be aware that there are actually 3 electric grids in the United States. Each one is a synchronous 60-cycle system. There are short connections between the 3 systems that are AC, DC, AC. And Texas, of course, likes to be its own nation, and that's why they're sort of singled out as a separate electric entity. This just shows a very small subset of the higher voltage lines in the country, and it does not show the DC lines that are prevalent as well. There's a few DC lines in the country. Important thing to remember is that in the electric utility business, if you're doing research, is there's 4 classes of utilities that have really different mission statements, so to speak. There are, of course, the investor-owned utilities like Duquesne, which serves this territory. PG&E, Pacific Gas Electric, is where I'm from in California. But there are also federal utilities like TVA and Bonneville. There are municipal utilities, like the city of Palo Alto is a municipal utility. And then there are cooperatively owned utilities. And they all have different mission statements, and they interconnect with each other. And within any one of these so-called interties, all 3 systems are interconnected in an AC, and in some cases DC sense. So there's standards and procedures to make sure that all these different types of utilities work together. And in fact, the research that a co-op utility may need to be performed is quite different from the research that an investor-owned utility would need in some cases. Now, in other cases, they can overlap each other. This picture just shows the average week of the country where you have the load going up and down as people wake up and go to sleep. Important thing about this picture that I wanted to point out is that we need a lot of nuclear power to grow in this country, to particularly respond to the CO2 crisis. Secondly, we need a lot of energy storage, and energy storage is this light blue color here, and I've ran a simulation a few years ago where there's a lot of energy storage in this particular grid, and it is being charged mostly with nuclear and discharged to reduce the consumption of oil and gas for cycling and regulatory duty. And I would say that in the future we're going to need to figure out how to install much more storage to take advantage of the renewable wind and solar and other non-CO2 bearing generation types. But it's this daily change of the load that causes a huge economic benefit to have different types of power plants, nuclear for base load, intermediate duty plants in this region for cyclic duty, and then peaking plants that just operate a few hours a day. And if it wasn't for the fact that we had such a cyclic load, we could actually operate and build a system that would be much more efficient than it is today and produce much less CO2. But as long as people go to sleep at night and wake up during the day, we have to build a system that will respond to that type of load. Big drivers industry. Jay's involved in some of these meetings with various regulators and all. We have an impending crisis within the electric utility infrastructure itself. in that the load growth over the last decade has been 35%, whereas the capacity in generation, in fact, even less in transmission, the wire side, is only at 18%. So we've only been building about half as much as we need, and we've been using up all the fat that's been built into the system by our forefathers. And as a consequence, ultimately, we're going to have some significant changes in how we use electricity to make it more efficient, and to actually build more wires and build more generating plants to even come close to the kind of standard of living that we've grown accustomed to have. There's another big change in the industry. There's been a lot of wholesale buying and selling of electricity that moves large amounts of power across the country, mostly within individual, those three interties I showed you earlier. And this is a huge number that's even getting larger. Big difficulties in siting new transmission because of rights-of-way issues. I may think electric transmission line looks beautiful, but most other people may not think so. But we have to figure out a way to take advantage of the rights-of-way that are existing today and put more power over those same lines, or higher the voltage over those same territories. And there's going to be a big focus in the research realm to actually take advantage of the existing rights-of-way and just to manipulate the electrons to move across the grid in a much more efficient fashion. Climate issue is certainly going to transform the electric utility business, and there's a huge opportunity for a lot of research as well as business. Somebody's got to finance all these new construction and take advantage of the technologies that are there. States, you've probably heard about deregulation in the electric utility business. This experiment started in California a few years ago. It was done very, very poorly. I'm actually paying a great deal of extra taxes because of the way deregulation was set up in the state of California. And in fact, it never really was deregulation. It was a re-regulation. It was a different set of regulations that occurred, and it really wasn't very well planned. It wasn't simulated at all. It just, people, in particular California, just jumped in and did it without understanding the consequences. And in many cases, they lost $50 billion plus. The transmission has been re-regulated at the federal level. FERC has a mandate now with the Energy Policy Act. NERC is got a new organization. It's called the Energy Regulatory Authority, or organization, ERO. And that's still being sort of ferreted out. There's still a lot of uncertainties just how all that's going to work out at the federal level. At the regional and the city level, the distribution systems, the lower voltage systems, they're still going to be regulated by the states, not the feds. As long as electrons don't go across state borders, in general, the states have authority over all the rules for that. So there's been a lot of changes, literally, in the last 2 or 3 years. We have about, in EPRI, we have about 700 members. 90% of all the electricity generated in North America comes from utilities that are members of EPRI. EPRI is a not-for-profit organization where I work. We have also about 130 international groups that fund EPRI, but about 85% of all the revenue that comes into EPRI that funds our research comes from U.S. utilities. Either they be investor-owned or federally owned or municipal or rural cooperatively owned. Most of the money EPRI, I'm sure, in fact I know, does come from the investor-owned utilities because they generate most of the electricity. We do work across nuclear and fossil generation. We call the wires business affectionately power delivery. A lot of work going on environment, and then we have what's called a consumer side of the business, the end-use customer side, and we do research even on light bulbs and motors. EPRI sort of sits in the middle of a matrix of efforts that are running on across the country all the time. There's a lot of national laboratories and universities that get federal money to do basic research. Mostly EPRI gets only into a subset of that type of basic research. And some of that comes from the group that I'm working at in the innovations sector of the business. Most of EPRI is sort of funding research in this mid area between commercialization and the basic research. We get involved in the integration, the application, try things out, help fund demonstration projects. We always do things in collaborative teams of utilities. where we take advantage of the group of utilities that fund EPRI, and any one of them may only pay 5–10% of the bill, but together we can fund some fairly large projects. Overall revenue this year is somewhere around $360 million. And for a voluntary, not-for-profit organization, it's not too bad. Our particular role in any given technology, either it be light bulbs or nuclear power, really depends on the specifics. As often as possible, we try to team with various government organizations, if possible, to leverage our own funds. Some of the R&D challenges besides CO2 issues, we have a whole program dealing with the so-called self-healing grid. We affectionately call it IntelliGrid. But the concept is to move the existing electric grid structure, the operation and control of the electric grid across all these 3 major regions of the country, into a more automated sensor monitoring system so that it can in fact heal itself without any human interaction. Build in intelligent operating algorithms that are monitoring phase angles between voltage and current and monitoring voltage stability indices and putting in extra capacitors or energy storage or whatever any moment of the day. And this effort, the self-healing grid, is going to go on for very many years, and we're involving some of our international clients as well. Transmission bottlenecks. There will continue to be, certainly in the near term, a lot of rights of way that have transmission lines that in the peak summer period are just overloaded. And in fact, when transmission lines get overloaded, they get overheated and they start sagging, and that's what caused the blackout of August 14, 2003 that took out most of the northeast of this country with a $50 billion cost to the society. So we are doing and will continue to do a lot of work to reduce.
Say that again.
$50 billion.
That's an order of magnitude more than any estimate I've heard. Where'd you get that?
Well, this is a number that incorporates more than the reports that have come out. Most often you hear 5 billion. But in fact, if you looked and you accounted for some of the so-called secondary effects of blackouts, of that particular blackout, it's on the order of 50 billion.
Okay.
But we don't publish that.
Report on that?
No, we usually say 5 billion.
We need to get together on that.
Okay.
Because that's a big difference, that order of magnitude.
It is. It's a factor of 10, obviously. Calculating the cost, the economic cost of blackouts is an art. It's not a perfect science today. In California, where I'm from, the blackouts that we experienced around 2000 just due to poor re-regulation, the numbers were somewhere around $4–5 billion. But in fact, the state of California, to pay for the electricity that was needed to serve the customers, had to float a $50 billion bond. And my taxes are paying to pay off the interest on that bond. So yes, there's a lot of uncertainty as to really the cost for blackouts. I think the most important thing to recognize, it's very large. And generally the costs for anything that goes wrong in the electric system far exceeds the cost for doing research or doing even construction of new transmission lines or new generation plants to make sure we don't have blackouts. So we can debate as to what the actual cost is, and a lot of people do that. Another big area of research is what we call the consumer portal, and you don't see it much here yet, but it's coming. And the electric utilities are slowly recognizing the importance of connecting in a communication sense with their customers, so that you as a customer can go to a display either on your computer or on your wall and actually find out what is the cost of electricity any time of the day, and find out from the utility any incentives they may have to help you make decisions to turn your washing machine on a Sunday evening rather than a Monday afternoon, etc. And I would say there's going to be a lot of work in the consumer portal area to manipulate price signals and incentives in not only residential customers but industrial customers, such that we can start changing the shape of that load curve that I showed you earlier. And this is a big area of research. Clark Gellings, who you know, Jay, is intimately familiar with that. Another area is providing the AC sinusoid with a much less per perturbation, so to speak, in voltage sags or frequency dips or short-term interruptions. All of us have experienced cases where the lights will flicker during a thunderstorm, or maybe even the thunderstorm isn't here, it's somewhere else. And there's a lot of automated systems that go into place to reroute all these electrons to your particular room. The consumer has many more devices that we call digital grade in nature, and they require much purer sine waves than we've ever had to generate in the past. So there's work going on in EPRI's power quality area to figure out how to provide the consumer a much more reliable source of electricity. And there's a whole area of research in that domain itself. The plug-in hybrid vehicle, emphasize the plug-in. You're familiar with hybrid vehicles. They certainly have better use of gasoline, but the Institute, being the Electric Power Research Institute, we're convinced that we should take a hybrid vehicle and actually have it plug into your household 110 volt AC line, and you should be able to have much better mileage as well as much better efficiency in the overall experience of driving. So you'll see a much larger impact in the future with plug-in vehicles, I would say. There's a big area at EPRI going on in that discipline as well. This is just a few of the many bullets that I could bring up on this slide, but we also refer to a communication superhighway that would marry with this consumer portal. And one way to enhance the self-healing grid concept is to have a much stronger communication system. So phasor measurements, frequency measurements around the country, real-time operator assistance and running the grid. We're going to have, I think, in fact, I'm almost positive that the communication systems that utilities use today are going to be completely revamped in the next 10, 15 years or so. That's just a few of the areas. Now into scenario planning. I was chartered about a year and a half ago to look across EPRI's research portfolio across all the divisions of the Institute and make recommendations with advice from our members. What should EPRI's portfolio gravitate to in the future? And there was a huge debate between me and many others as to trying to predict the future. That's a losing proposition, generally speaking. So what I came up with the help of a few others, is really a set of scenarios for the future. And there's 4 quadrants to this chart here, and on the horizontal axis is one of the most important variables electric utilities deal with is the price of premium fuels. In this case, I chose the price for natural gas. Low natural gas prices over here, high natural gas prices are there. On the vertical axis is the cost for CO2 emissions. Right now the cost is dead zero. In France, it's an open market on CO2 and the prices vary from $5 to $25 a ton, a metric ton. But if the electric utilities move from this so-called quadrant here, where the price of CO2 is maybe even negative to zero, and the price of premium fuels is somewhere around here, we're sitting in this so-called digging in our heels box. This is what we call this particular scenario. And more than likely, we're going to soon move up to this quadrant of business conditions where there will be a price for CO2 and the price for natural gas may be a little higher than what we have today. So there would be an R&D portfolio here that would really hopefully come up with more efficient ways to burn coal, more incentives to reduce the licensing time for nuclear power plants, and more renewables, more solar, more wind. Down here you wouldn't necessarily have as much nuclear power requirements. Likewise, if we ended up in a scenario over here where there's all of a sudden there's a glut of natural gas and oil on the market, God forbid that we might get down to our cheap fuels in the past. I say that facetiously, but if we ended up in this scenario in the future, you would have a different set of R&D objectives. And likewise here, we call this one the supply to the rescue. You would have very low prices for fuel and very low prices for environmental emissions of CO2 and the like. And we'd have tremendous new generating plants not even concerned about environmental consequences. So there'd be a lot of gas turbine, a lot of combined cycle research, a lot of new plants that wouldn't rely on nuclear. So I've come up, and hopefully I'll have time at the end of this presentation, I have a whole set of projects. What are the R&D opportunities for each of these 4 quadrants? Secondly, there's a lot of other variables that could impact the electric utility business and the R&D needed to support it if certain so-called wild cards occur. What if somebody invented a room temperature superconductor? What if we could never store any nuclear waste fuel rods in Yucca Mountain's repository? What if? And any one of these other kinds of events could drastically impact the electric utility industry too. And in fact, I'm working this year on figuring out with a bunch of other advisors just how to respond to some of these so-called wild cards. So one might say, well, then what do you do? Do you project, do you say we're going to stay in this quadrant? We're going to move to this? Do we move this? What do you want to do in the future? Personally, I've recommended not to bet on any particular future outcome. I'm telling people that they should hedge their bets and have a set of projects related to this domain, et cetera, et cetera. So now you can bring in your decision theory from your coursework, if you wish, and say, well, what probabilities do you have for each one? And you could put down a so-called optimal research portfolio. But in fact, each utility that funds EPRI has their own desires. They have their own local conditions. Some utilities don't have any concern with environmental conditions, others do. Some utilities are mostly nuclear. Some utilities are mostly coal. Some utilities have a lot of oil and gas in their generation. So each utility actually views these set of recommendations through their own filter. And ultimately, through our membership and through our advisory committees, we'll go through a revamping of what our R&D portfolio should be for this year, for next year, and in the future. And that's really what's happening. So don't look to me to tell you what the future is. I'm going to tell you it could be any one of a number of things. Now, what are some predetermined elements? I mean, there's a lot of things that are going on in the background that you don't really have much control over. Not much. One of them is uranium prices. They're slowly increasing, but it's generally pretty stable. The aging infrastructure. Our electric grid is extremely old. I mean, going back to Edison, actually. But in modern times, most of the transformers and wires and generating plants were built in the 1960s and 1970s. So the average age of a transformer today, a high voltage transformer, not the one you see next to your house, I'm talking about the big transformers at big substations, they're about 42 years old today. Their design life was 40 years. So we're going to have to replace thousands and thousands of transformers. Most of the transmission wires are still pretty good, but we're going to have to replace them with wires that carry more current but at the same temperature. So we have to deal with an aging infrastructure. We have in this country an abundance of coal. It's dirty, it produces a lot of CO2, but that's probably, well, in fact, it's about 55% of all generation in this country comes from coal. There's huge political and financial interest to continue to use this coal. So we have to accept that. So we got to clean it up. We're not going to get rid of it. We just have to figure out how to capture CO2 and sequester it underground or in other formations. That's a big R&D topic that EPRI's working on. Environmental regulation, generally speaking, it's going to continue and probably get stricter, certainly with CO2. Domestic gas supply. In this country, we are virtually out of natural gas. There's still a little produced, but the bell-shaped curve for the production of natural gas is far to the right now. We still have some oil produced in this country. It's also depleting. But we're going to have to import most of our natural gas. That's going to be expensive and dangerous. Renewables. Most states have what we call renewable portfolio standards. Really what that is a name, a little shortcut name for regulating the amount of renewables a given utility has to install. So in the case of California, we have to have 20% of renewables installed by 2020. In the word renewables is counted hydroelectric as well as wind and photovoltaic and biomass. Renewables.
Not in all states.
Not in all states.
In fact, not in the majority of the states that have renewables. High-head hydro counts only in 3 states.
Yeah, well, I'm talking about California, but the bottom line is that there will be requirements that utilities have to install a certain percentage of their generation mix with a certain percentage of renewables, and that's a state by state issue. That's causing a lot of utilities to invest in wind systems, in solar systems, even though they are not economically attractive today as compared to some other alternatives, because they just have a mandate to install a certain amount. Commodity prices to build transformers, to build pipelines, to build power plants, it takes a lot of steel, a lot of copper, a lot of concrete. All these prices have gone up tremendously in the last 5 years. A transformer today that I used to buy for maybe $2 million for a 200 MVA transformer is now costing about $5 million. It's gone up more than a factor of 2. That's going to continue. Local distribution will likely stay as a monopoly. Local distribution utilities. So those are just some of the background conditions that we have to live with. The technology space, this sort of is a broader mix of words for some of the examples I showed earlier. One thing I really want to focus on here is that the cheapest way to reduce CO2 in the nearest time period is to increase the energy efficiency across the entire spectrum of generation, transmission, and use. In this country, we have a very wasteful sort of habit of leaving lights on, not installing fluorescent lights when we should, replace our incandescent lights. We've had such cheap fuel for so long, we really produced an infrastructure that isn't really quite efficient. And every one of us could buy more efficient refrigerators, more efficient air conditioners, fluorescent lighting, etc. This is the cheapest and nearest term way to reduce our CO2. The longer term way is to go to nuclear and to generation and coal generation. And to some extent, where you can, you should install wind, but you get a lot of wind fluctuation that produce fluctuating power surges, and then they have to be compensated by the operators. So I would say this area is going to be growing a lot in the research discipline. I'm sure nuclear is going to grow a lot in the research area as well. In the report that I'm going to be giving Jay, there's a list of 20 specific topics and a whole list of research topics under every one of these 20 topics. I presented this to an executive committee last December, and then included a voting prioritization based on their perceptions. And that's also in the last chapter of this report that you'll see. And I put this as unranked. We actually ranked all these 20 items based on CEO comments and surveys that we did at EPRI. Okay, now just for a few examples. And these are just really a very few sets of examples. I chose this first one because it's a new sensor. Sensors have to monitor not only the equipment, but also the grid, so that operators can control it better. This particular sensor is actually designed to monitor gases that are dissolved in the dielectric fluids of transformers. And we found out, based on basic research, that certain gases that are dissolved in the oils at a very, very low level are very well correlated with deterioration of the paper insulation, of the actual clamping of the cables in the transformers. So we use these sensors to monitor the health of the transformer. And in some cases, we install these things and they give us real-time signals rather than just getting a signal in a grab sample environment once a week or once a month. And this particular sensor uses some nano metal oxides on it. So it's about the size of your thumbnail. So it's very, very small. And this is being commercialized now. It's a very, very nice example of some successful research. Another example of some nanoparticles is using nanoparticles to increase the dielectric properties of insulation used for underground cables. A lot of cities, Pittsburgh I think is one of them, have their underground cables pretty well overloaded in the summertime. And we need to put more power through those cables to not to necessarily install overhead transmission lines. There's only just so much space underground in these underground conduits. They're very expensive to build. And what we want to do is take out some of the old cables and put in new cables that have much more throughput. And by what we found is this: by injecting some nanoparticles in the solution of the composite polyethylene material used as the insulator, we can actually increase the the dielectric properties by 40%. So we envision commercializing this with an underground cable manufacturer and actually installing cables with much higher throughput so we can not necessarily have to dig up your streets again to lay cables underground. Nanotechnology is a relatively new area that EPRI got into a few years ago, and it's already producing some very practical results. It's very interesting. Here's an example of a superconductor used to limit short circuit current. Let me explain what that really means. Generally speaking, any operation of an electric grid will experience short circuits over its life, either because somebody dug a hole where they weren't supposed to, like a backhoe cut a wire, or a lightning strike hits a tree, but that lightning goes into the ground and then it melts the underground cable nearby, and then that cable is short-circuited. We have already automated systems to monitor huge increases in current and then open the circuit. So we have what's called current limiters or circuit breakers that automatically open circuits when current gets above certain thresholds. What's happened with our industry is that a lot of independent power producers are now installing generating plants near cities or in cities, and the need for increased current carrying capabilities for the short circuit current limiter has actually gotten increased by factors of 2 or 3. So we have to build better short circuit current limiters. So that's why this project was even thought about. There's a couple of ways to build short circuit current limiters. One of them is using a superconductor, because the superconductor has a very nice property that it is almost zero resistance when the temperature and magnetic field and current are below certain thresholds. And anytime one of those 3 gets above a threshold, the resistance of that superconductor jumps to very high numbers. So that's a very nice practical way to limit current using superconductors. So we put together a demonstration project. This is I think it's a liquid nitrogen dewar, and there's a superconducting cable in there, and this is the device used to limit the current. Another way is to actually build a solid state circuit that measures the current and then just opens a thyristor or gate turnoff transistor, and it limits the current without any superconducting. But this was a superconductor used for short circuit current. Okay, CO2. One of the first things you got to do at a coal plant if you want to get rid of CO2 is figure out a way to isolate it, to take it out of the exhaust. If we could take carbon out of the coal ahead of time, we wouldn't have CO2, but it wouldn't burn either. So the only way to get CO2 out of a coal plant that we know of right now is to take it out in the exhaust stack. Very expensive proposition. The so-called commercial way to do it today is with a stripper, and this device in itself consumes about 30% of the power that the plant produces. So if this is the only technology available to actually sequester, not sequester, but to identify CO2 and then hold it in a place before you sequester it, your price of electricity for coal is going to go way up. So we're trying to figure out better ways to actually do this process. One way is to cool the whole thing off and to use a different set of chemicals, and we think we can get this 30% penalty down to maybe 15%, but it's still going to be a very, very expensive proposition. A lot of work is going on today and will continue to go on in how to capture CO2. Here's a solid state transformer. One of the reasons transformers are so expensive is they use a lot of copper. So the question is, can we use our solid state devices that are in our laptops, can we use them to somehow configure a transformer that can process a much higher voltage and a much higher current? The answer is yes. It just has its own difficulties, but we're doing research in how to replace the transformers with just a solid state version. And if this works, what I predict is that we'll end up not only having AC at our household, we'll end up having DC sockets in our household as well. I certainly envision that your electric plug in your house will ultimately have a DC source as well as an AC source. And instead of having AC-DC converters for all your laptops and your TV and These lights themselves are actually DC, they're not AC. We have a lot of AC-DC converters all over our infrastructure today. Ultimately, but this will take a long, long time, we could end up having a DC set of circuits in your neighborhood as well as an AC set of circuits, and actually make the delivery system much more efficient. If this transformer works, that'd be one way to make that happen. The last example is plug-in hybrid vehicles. This is a big program at EPRI, as you might expect. And we're working with Daimler Chrysler, and we're already built a few of these vans, and they're under test today. So I actually envision in the long run, we're going to see commercially attractive plug-in hybrid vehicles, where when you get into your car or when you come to your university or you come to work, you're going to have a little credit card that'll identify your car and everything, and you're just going to plug in your car and you're going to have an automated system tally up hopefully a small electric bill to recharge your car. I mean, most electric vehicles, one of their big nemesis is they don't have a lot of range, because to carry around a big battery pack is heavy and voluminous. And ultimately, we're going to have to be able to charge our cars at work or at the university as well as at home. What would be nice is that while it's plugged in, if there's an emergency condition, the electric utility needs some energy to take care of the peak loads during the afternoon, your electric vehicle, if you so choose, you're going to get paid for when the grid needs some of your stored energy in your car. And there'll be limits as to how much the electric utility you allow them to take from your car. You still got to get home at night. But I envision if a communication system is put in place, we're going to be making money when our cars are plugged in at work and the utility needs some extra stored energy. There could be, if there's millions and millions of these plug-in vehicles, that'll be a source of peaking power and reduce our needs for oil and gas to provide peaking power. So that's the future. So let's see, what time is it right now? Oh, I got about 10 minutes, I see.
Got about 5.
Okay, about 5 minutes. Good, I'm near the end here. The TI program here, this is a chart that just sort of gives you a simplified flow diagram of how research is done at EPRI, probably done in other places similarly, but we have a program called Technology Innovation, which is at the very beginning of the process, where we analyze new materials, new concepts, new technologies. We do a lot of small little studies. And then through a filtering process, we ultimately figure out which products to help develop, maybe develop a system architecture, do some demonstrations, write codes, help write regulations. We go through commercialization processes with vendors, et cetera, et cetera. The TI program, we are hiring 8 people this year in '07, 2 in nuclear, 2 in power delivery, 2 in environment, and 2 in fossil generation. And they stay in this group for about a year. It can be anywhere from 6 months to 18 months, but on average about a year. And we train them as new graduates to work in a particular division of EPRI.
And when you say new graduates, what level are you hiring?
PhDs and master's students. I prefer PhDs, but we do hire master's students too. And EPRI, going back to the bimodal distribution concept that we just talked about earlier, EPRI has an aging infrastructure itself, just the way the electric utility business does. And we are determined to bring in fresh, new, young students and get them involved in the electric utility business in high voltage, high current, power plant, wires business, environmental issues, etc. And last year our program had 4 students. It was so well liked by the management of EPRI that we were told to increase its size to 8. Maybe next year we'll have 16, I don't know. But we are certainly in the process of hiring students, and I'm going to interview some of you later today. That was worked out by Jay and his assistant. But if anybody wants to talk to me privately after the meeting or whatever, just give me a card with your email address or phone number, and we can talk in the future. There should be a little poster somewhere around here of some of the areas that EPRI's hired in. Did we send you a little poster? Okay, I'll send you a little poster. You can stick it up on one of your bulletin boards. But the TI office has its own little group. I manage those 8 people. And then there's also groups in our nuclear group or high voltage distribution transformer. I mean, we hire people in other groups as well. But I'm specifically oriented to try to get new students. Most of the other groups prefer to hire seasoned, experienced engineers that have been in the electric utility business for at least 5 years or more. We generally have a requirement in the nuclear sector or whatever to hire people that have experience. But in our group, we do just the opposite. Okay, now it depends on how much time we have left. I actually have a little recording here. Most people have never heard Tom Edison's voice. And maybe I thought you might want to hear him because he had something very interesting to say. And I'll go ahead with that rather than get into some of the other technical details. But before I do that, let me tell you what Tom Edison said once. And this is a quote that's not often rewritten. He said, "In periods of profound change, the most dangerous thing is to incrementalize yourself into the future." Don't think incremental, think, basically he's saying think out of the box. In the jargon we have today, your new improvements should be revolutionary. And he certainly followed that process. Another nice thing about Tom Edison is that he learned from his mistakes. I mean, even I was a student once, but you guys and gals as students, errors, mistakes are frowned upon. But what Tom Edison learned, and I offer this to you to learn as well, if you haven't, is that learn from your mistakes. Because you can succeed in business by keeping a record and not making those same mistakes again. It's nothing wrong making a mistake once, maybe even twice, but the third time, now you got a problem. But he learned from his mistakes. He tested thousands of filaments for that little light bulb, and it revolutionized the world, there's no doubt about it. Next little quote that you don't hear from Abe Lincoln much, but he did say this: "The best thing about the future is that it only comes one day at a time." People think about the future as something long-term, something way out there. It's now and tomorrow. The future is today. So what I want you to do is listen to this tape, and one of the things you're going to hear is that he makes comments to some disastrous failures that occurred in the business. And he refers to, what he's referring to is a guy by the name of Cyrus Field, who spent millions of his own money to lay the first underground cable from England to Canada. Why? Because he wanted to sell stock quotes to the Americans and the Canadians. And Canada was the least distance path to get from England. And then he also references Morse of Morse code fame, and he always also references Ben Franklin of the famous kite experiment. So just listen to this, and I don't have a microphone here, so you're going to have to just listen very carefully.
Ladies and gentlemen, those of us who began our labors at the operator's key 50 years ago have been permitted to see and assist in the whole modern industrial development of electricity. Since the remarkable experiments of Morse in 1844 and the unsuccessful efforts of Field in 1858, there have come with incredible rapidity one electrical art after another, so that in practically every respect civilization has been revolutionized. It is still too early to stand outside these events and pronounce final judgment on their lasting value, but we may surely entertain the belief that the last half of the 19th century was as distinct in its electrical inventions and the results as the first half was in relation to speed. The lesson of the Jubilee of the Atlantic Cable of 1858 is one of encouragement to all who would add to the resources of our race and extend our control over the forces of nature. Never was failure more complete, never was higher courage shown, never was triumph more brilliant than that which since 1866 has kept the old world moored alongside the new by pulsating cables of steel and copper, the family ties of the civilized world. When I look around at the resources of the electrical field today, as shown in this exhibition, I feel that I would be glad to begin again my work as an electrician and inventor, and we veterans can only urge upon our successors, the younger followers of Franklin and of Kelvin, to realize the measure of their opportunities and to rise to the heights of their responsibilities in this day of electricity.
Okay, that's it. Anyway, that's Thomas Edison in 1908. He was 62 years at the time giving a speech. And that's what I wanted to end with here, give you a little motivation. That guy actually saw where he was going. He had this vision of the future, and he lived to see at least part of it to come true. Okay, any comments or questions?
Thank you. Questions?
I have a question.
Sure.
One of the last two slides we talked about was technology development, and towards the end is commercialization. So I just wanted to hear any of your comments that have to do with, I mean, you're dealing with a type of environment where there are lots of different types of businesses or government that you're dealing with. Yes, they're interested in the research, and at what stage do they get involved? You said they direct some. So how is that integration occur along the different lines of your clients?
Okay, let me repeat your question in a little shorter phrase. You want to know how the research actually gets implemented. Is that your question?
Right, towards the other end.
Okay, towards the other end. Okay. The simple answer is that it depends on the particular technology. Most of the time, we, EPRI, work with a lead manufacturer, either in the development of the projects, or the development sometimes, or after the universities and EPRI do some of the core research, we bring in the manufacturer to actually manufacture the first pilot scale or lab scale demonstration of the results. So we'll go from small to medium to very large scale, and that's when we work with the manufacturers and the vendors, because ultimately the utilities have to buy this equipment from a credible manufacturer, either it be Westinghouse Electric or ABB, say Brown Boveri, or Siemens or whatever. So it's critical to get the manufacturers involved in that later phase of the efforts, and that's the way it happens.
Question over here.
Who owns your intellectual property?
Who owns the intellectual property? Actually, EPRI always owns the intellectual property. It's a matter of who we license the results to and what kind of royalty payments we want back when we do the license. That's a negotiation. It turns out that I'm actually in charge of that effort at EPRI right now. It's a very, very time-consuming process. But we have a set of patent lawyers that license our intellectual property. We always own it, but we license the results to other people. Good question. Anything else?
Okay, well, thanks.
Okay, sure enough. Whoops, yes.
You mentioned a lot of 85% of your money comes from U.S. utilities.
Yes.
And my guess is, I don't have a breakdown, EPRI worldwide, a lot of that money from outside is a few countries specifically when we're talking globally. How would this apply to, say, India or China, because you're focused on them, and other developing countries where we really have opportunities to think of electricity differently than business as usual?
Okay, well, that's true. The answer to your question is mostly the big manufacturers that carry forward with some, let's say the plug-in hybrid vehicle or a nanotechnology for insulators. The manufacturer will sell that product internationally. It's not just sold in their particular country or in the U.S. alone. So it's the manufacturers that really deal with the...
That's a supply side. But in an integration in business processes and thinking, I mean, utility R&D budgets in developing countries are, if we think they're bad in the U.S., try negative. I mean, practically.
Well, the only way that those types of countries will find out about this is either they read some of the stuff we let public, which is a fair amount, or they join EPRI itself. It turns out there are some Chinese funds used in our research. Not much, but a little bit. The big utilities that fund EPRI are EDF in France, Polish Power Grid, Venezuela is funding EPRI, Canada, of course, is a big funder, Taiwan a little bit, but most of the efforts, 85%, are strictly U.S. We EPRI, our main client are U.S. utilities. We do not go out of our way to get funds specifically from individual countries. It's just not our charter. Our board of directors is primarily composed of U.S. utilities. There's, I think, one foreign utility on our board, and that's EDF, Electrique de la France. So we really don't go out and try to get change or modify the rest of the world. That's not our mission right now.
Anyone else? Thank you again.
Okay, good.